SwayamPrabha. Digital India. Educated India.
Hello, welcome to this lecture of Biomathematics. We have been discussing about diffusion in the last lecture, where we used ideas from vectors and calculus to derive the diffusion equation. We said that just by taking the continuity equation, that the current from one side to the other side, when you think about the current, we said that for the concentration to change at a particular place, whatever the current, that is the flow that is coming in, has to be can't be equal to the flow that go out. If they are equal, the concentration at this point will not change. And from this just simple common sense argument, we used mathematics, which is we said it's like a language. So we used mathematics basically to express this idea that the current that flowing in has to be different from the current that is flowing out for the concentration at a particular point to change. And from this simple argument, we derived an equation, and that is the diffusion equation. That equation governs the diffusion of particles, as we discussed. Today, we will discuss a little more about diffusion. There are very important relations that is related to diffusion. So, we will discuss some very important and interesting results associated or resulting from this equation, which are related to diffusion. So, today's lecture is basically again related to application of calculus and vector algebra in biology, and we will again discuss diffusion. So, today again we will continue discussing diffusion, and we will derive some interesting results, interesting expressions related to diffusion based on what we learned so far. These are very important relations, very famous relations, very useful in biology and in many other fields. So, let us get started. So, we said that when you, so what is shown here is a tube. So, you have a tube and this long tube, and you introduce some particle at some particular position. Let us call x as the length along the tube. So, this is x equal to 0, and this is x equal to 0, and as we go, as x is equal to increasing and x is decreasing. So, let us think of this as an x axis, and there is in this tube we are introducing, let us say we are putting some ink molecules, and there is imagine that there is water in this tube, and we are introducing some ink molecules or protein molecules in this tube. So, that is shown here, and what is shown at the bottom here is the plot of concentration as a function of the x. So, this is x equal to 0. So, at this moment the concentration is only at x equal to 0, somewhat almost like a line up with maybe a little more width, but essentially it is just like a line up. So, which says that the concentration is only the concentration everywhere else, here everywhere the concentration is 0, and the concentration is non-zero only at x equal to 0. Only here you have particles, and here you have no particles. So, this is what this picture is written in kind of in the form of a graph here. That is what is shown here. Whatever shown here is written in the form of a graph here. Basically, what you have here is that the physical picture is that you have a tube, and in the middle of the tube you have some protein molecules. some the concentration of the protein molecules is only at x equal to 0, and nowhere else you have this protein molecules. How do we represent this kind of a thing mathematically? What is the equation that you will write for representing things of this fashion in a mathematical form? So, we said that anything that we speak or any idea that we see or any physical idea, we can represent in the form of equations, and that's kind of a language in itself. So, how do we say this mathematically? The fact that you have only concentration at one point and everywhere else it is 0. It is shown graphically here, just a line here, and everywhere else this is 0. So, the way to show this mathematically, it turns out that, so if you have x equal to 0 and you have only at this particular point, this is shown by, so this is a function, and it turns out that this function can be written as delta of x. So, this delta, this famous function, this is called, this is mathematics, this is called Dirac's delta function. Basically, this represents, this is basically precisely to say what we just said, that you have only something only at some particular point, everywhere else this is 0. There are some particular properties for this, for the Dirac delta function. We would not go into this, but what I am trying to say is that you can represent this mathematically using this delta function. So, the concentration that you see here, C of x, if you wish, can be written as a Dirac delta function. C of x can be written as, so you can say C of x is proportional to, is directly proportional to the delta of x, is like Dirac delta function. So, this is a way of telling this mathematically. So, now let us think about, let us think physically for the moment. Let us just keep the mathematics apart for a moment. And so, we know that you have a tube here and we have some protein molecules here, and there is water in this. You can think of this as protein molecules or even ink molecules or any molecules here, and we call it at time equal to 0. This is what the thing you see. Now, think of this, as the time goes, what will happen? Let us say after 10 minutes, if you look at this tube, what will you see? You will see that these molecules would have diffused this way and this way. They just diffuse this way and diffuse this way. So, they would have diffused either along this tube. So, what do we see? You will see this. Look at here, they have diffused along this way. So, there are some molecules here, some molecules here, but still majority of the molecules here. So, this is what you see after 10 minutes. 10 minutes, after 10 minutes you see that there are many molecules still at the center at x equal to 0, and many molecules, a few of them are here and few of them here. And if you represent this graphically, you can represent it this particular way. The concentration, if you plot as a function of x, what you would get is that at far away the concentration is very less, and at the middle the concentration is large. So, forget what the form of this curve, what is the equation here, but there is some particular form which a mathematical, this is graphically, this concentration can be represented by this particular graph. That is, it is a peak at the middle, that means still majority of the molecules are in the middle, very few of them are towards the ends. As you go along far away from the center, either to the left or to the right, you have fewer molecules, and there is no particular reason that right is any different from the left, because if there are two of them, 100 or if there are 20 of them diffusing to the right, you might as well have 20 of them diffusing to the left. I mean, there is no symmetry. Symmetrical, they are symmetric, like left and right are symmetric to each other. There is no particular reason that left is different from the right on this particular tube. So therefore, the concentration on an average on the left and the right will be the same. There is no particular reason that more will diffuse to the left or more will diffuse to the right. So this function will be symmetric along x equal to 0. So you have a function which is essentially, so you at the to begin with, you had this x axis. So this is x going to, if you think of this, let us say you are going to plus infinity, and this is plus infinity and this is minus infinity. Let us say this is x is going this way. To begin with, you had just one line as a concentration. So this was a concentration to begin with. So this is t equal to 0. Now as the time went, the concentration, so if you take this x axis, this is minus infinity, this is plus infinity, this is 0. So this is 0 here. What you would see is that you would see kind of a nice symmetric thing like this. I mean, maybe what I drew may not be perfect, but I wanted to have the peak at 0. Here this is peak at 0 and symmetric about this. As it goes to infinity, so this is the concentration as a function of x. As it goes to infinity, the concentration will go to 0. So at you know that in the tube, if you look at the tube here, far away at infinity, you will not find anything after 10 minutes, because it would not have yet reached infinity. So important point, C at, look at here, C at infinity is 0, C at minus infinity is also 0. So that means here and here the concentration will slowly is actually 0. Far away the concentration is 0, and at the middle you have maximum concentration. So you have, after 10 minutes this is what you expect. But the important point to note is that at infinity, C at infinity and C at minus infinity has to be 0, because you can imagine after some 10 minutes the concentration, it would not have reached infinity. It wouldn't, if you look at a distance far away, if you look at a far away distance, it wouldn't have yet reached that far. So the concentration there has to be 0. So by knowing just this, that it has to be symmetric and that the concentration, the molecules wouldn't have reached at infinity or far away, we can derive very interesting results. This is some two physical things we have to know, that after it will have such a shape and it will have a symmetric shape around x equal to 0, and that concentration will be 0 far away. I mean, it would not have reached there. No molecules would have reached far away from the initial position. If you look at far away from the initial position, after 10 minutes, molecules would not have reached there. After any time, after a finite time t, it wouldn't reach some infinitely far distance. If you know this much, we can derive some interesting stuff. So what did we say? We said that we have, what did we say? We have some concentration, and C at x equal to infinity is 0, C at x equal to minus infinity, it is 0. What does this mean? If you have in a pipe, if you had a pipe like this, and if we had some molecules here, after any finite time, they would not have reached far away, infinities and minus infinities. Here the concentrations will be 0, here also the concentration will be 0. They will be still diffusing somewhere near the initial point. So, this is finite time. At any finite time, after 1 minute, 2 minutes, 3 minutes, 4 minutes, even after 10 minutes, it would not have gone that far. It will be still at a finite distance x, the concentration. So, knowing this much idea, so now if you know that it would not have reached here, the derivative, let us say del c by del x at x equal to infinity, this will also be 0, because there is no molecules here, so c itself is not there. So, c cannot vary there because c does not exist there. So, del c by del x will be 0. Here also del c by del x at minus infinity, when x equal to minus infinity, this will all be 0, because there is no molecules. So, the change in concentration will be anyway 0. So, if you, by knowing this much idea, we can get some interesting results. So, let us go ahead and do this. So, now let me do some small, let us discuss another interesting fact. So, we know that we have a concentration C of x. So, what is integral C of x dx? So, at every point x, you have this concentration C. So, now what you are doing? You are doing summing over all the concentrations along x. So, that is integral C of x dx. So, what is this? This has to be the total concentration Ct. This has to be total concentration Ct, because this is the, now for simplicity, now let me define a new function called C tilde of x, which is C of x divided by this constant Ct. Just for some convenience I am doing this. This is just a trick, just for convenience I am doing this. So, if you have such a function, what will be integral minus infinity to infinity C tilde of x dx? This will be integral C of x dx divided by Ct. We know that integral integral C of x dx is Ct from here. So, this will be Ct by Ct, this will be 1. So, we have this new function, let us define, and this function called C tilde of x, which is the C of x divided by some constant number, which is the total concentration. So, this, what is the C tilde of x essentially? This is the fraction, in some sense, concentration divided by the total concentration. In some sense, you can think of this as a percentage or a fraction, or in some sense, this is like a fraction, but it does not matter what does it mean. It is just a trick. We have this concentration, we divide it by a constant, we can always divide by a constant, mathematically nothing changes, and we have a new function C tilde of x. Okay, so we did some tricks, we just did realize that integral C of x dx is total concentration, and we defined a new function called C tilde, and we called it C of x by Ct, such that the integral C tilde of x dx is 1. That means this integral of this becomes 1. Okay. We have C tilde of x. Now, let us go back to the diffusion equation. So, what is the diffusion equation? Diffusion equation is this equation that we described last time, that del C by del T at any point x and t, at any point x at any point time, at any point x at any time t is equal to d del square C by del x square. So, the change in the, how does the concentration change with time is this, and how does the concentration change in space? X is the distance, space variable, and this is essentially how does the concentration change with space, and this how does the space change with time. How does the concentration changes with time? So, this relation is called the diffusion equation. Now, let us look at a few properties that we defined last time. We define x average. So, here x average is integral x c tilde x dx. So, c tilde we just defined it as concentration divided by C t. So, this is some kind of a normalized distance, do not worry about this. So, this is the let us define some quantities called x average and x square average. What does this essentially mean? We will discuss this. We will discuss what does this essentially mean, what does this physically mean, but we can always define x average and x square average in this particular manner. So, if you do this x into c tilde of x dx and x square into c tilde of x dx, we get this x average and x square average. Now, the aim of this is to derive some interesting results related to the RMS distance of diffusing particle, the root mean square distance. So, this is the definition of x square average. So, typically you might have seen it many places that you might have heard of RMS velocity, RMS root mean square velocity. What is root mean square velocity? Like, think about you had gas in a box, and this gas molecules were freely moving in all directions. This ideal gas we had, and we could calculate, and in such cases you might have studied that VRMS, the root mean square velocity. This is related to the RT and temperature and all that. This is related to temperature. We have assigned something called RMS velocity. So, the definition of this is that V square average, this is root, there is a mean, this is mean, this is square mean square. So, and this. So, this is the definition of RMS velocity. You find the root, mean and square, root, mean, square. Similarly, here you have particle in a tube going this way and that way, they are diffusing, and what we want is x square average root. So, this is, you can say x RMS, the RMS distance, the root mean square distance that this particle will diffuse with time. Like, if you wait 10 minutes, what is the root mean square distance this particle will diffuse? So, let us think about just one particle here. Look at this one particle. This one particle can go a little here, then it here. So, on an average, we also can find out how much, what is the average distance and what is x square average. This is what we want to find out, and this is what we have defined here. So, let us we have defined x average as this and x square average as this. Okay, now let us calculate this. Now, how do we calculate? So, we had this diffusion equation, which is del C by del T is d del square C by del x square. I can divide both sides by C t. So, C by C t is C tilde. So, I can write this as del C tilde by del T is del square C tilde by del x square, where C tilde is defined as C by C t. You just divide here by a constant, here also by this constant C t, both sides. So, I divided by C t here, I divided by C t here. So, I divided by C t here, I divided by C t here. Since it is a constant, I can get this equation. Okay, so, now we have this equation. So, now that we have this equation, del C tilde by del t is equal to d del square C tilde by del x square. I can multiply both sides. So, first let us first calculate x square average. I can multiply both sides with x square and integrate. So, let us do this. So, there is del by del t, I multiply with x square and there is c tilde and is equal to d del I have x square I multiplied and I have del square c by del x square and I integrate both from minus infinity to infinity dx. So, what did I do? I just multiplied both sides with x square and integrated both sides. Nothing will change. I multiplied both sides with x square, I integrated both sides with respect to x. Now, here the derivative is with respect to time and this is a partial derivative. So, it does not matter whether I take the derivative outside and the integral is with respect to x. So, if the integral is with respect to x, you can take this del by del t outside, because the result of this is anyway has nothing to do with time. Sorry, this only depends on x. So, I can, whether I write x square del by del t inside or outside, it does not matter, because the integral is only with respect to x and this is a partial derivative. So, I have this kind of an equation. So, what do we have? I multiply, what did I do? I had this equation, I multiplied both sides with x square and I integrated with dx. This is what I did. Okay. So, let us write it down once more to be clearly. So, we had del by del t of integral minus infinity to infinity x square c tilde of x dx is equal to d into integral minus infinity to infinity x square del c tilde by del x square dx. This is what we have and this is what precisely we have it here. Now, what is this part? What is x square c tilde of, what is this? We just learned that we just defined this as x square average. So, this quantity we just defined this quantity as x square average. This quantity what I put in this around which I drew this line, we just defined this as x square average. So, the left hand side is del by del t of x square average. So, now what is on the right hand side? We have this. Now, you have some function x square, some other function del c tilde by del x square. So, you have two functions which depends on x and we have to find out the integral of this. So, we have minus infinity plus function x square and another function del c tilde by del x square dx. So, now we have to find the integral of this. So, something that we learned in calculus, we have to make use of this to get this. So, what did we learn in calculus? So, there is an interesting relation that we learned in calculus that we can make use here. And what is that? So, we learned that if you have two functions u and v, we have u of x and v of x. We learned that the derivative, we learned something called product rule. the derivative of this we learned that d by dx of u v is u into dv by dx plus v into du by dx. We learned this in calculus. This is called, we will call it product rule. So, that is derivative of product of two function is first function into the derivative of the second function plus second function into the derivative of the first function. This is what we learned. Now, we can integrate this just like this. So, we can just multiply with this and integrate this, and we can write this dx here. So, we can just integrate all throughout and get a relation. We can say u into dv by dx is equal to, so we can write. So, what can I write? So, look at here. So, I can write u into integral dv by dx is equal to, so this is equal to integral of d by dx of u v, d by dx of u v dx minus, I take this side. So, I just rearrange this term, I write this is equal to this minus this, I can take this term this side. So, u integral this minus this term, which is integral v du by dx dx, du by dx into dx. So, we are just making use of something that we learned in calculus, that we use the product rule, and using this product rule, look at here, using this product rule, we rewrote it in terms of integrals, and is the integral u dv by dx is this. So, in other words, I can rewrite this thing. So, dv by dx into dx, you can write this basically. So, let us write this a little more carefully. U into integral dv by, sorry, I just made a small mistake when I wrote here. This integral has to be here, integral u dv by dx, because this is what we had here. Integral u dv by dx is equal to d by dx of u v dx minus v du by dx. So, when I write a little more carefully, I have to write. So, what do I write? Integral u dv by dx is equal to d by dx of u v dx. So, derivative of function, integral of a derivative is the function itself, because integral we said is an anti-derivative. So, integral of d by dx of u v is u v itself. So, this is essentially the u v in the limits. So, if you have this integral, from minus infinity to infinity, all this integral will be from minus infinity to infinity. If this integral is from minus infinity to infinity, what you would have is in the limits minus infinity to infinity. Think about this. This is what you will get. Just carefully do this. Integral u v dv by dx into dx will be equal to u v minus integral v du by dx into dx. So, this is called integrate by parts. You have any function u dv by dx, you can write in this particular form. So, now look at this equation. What do we have here? We have in this side a function, let us call this. So, what did we have here? We had an equation which is del by del t of x average is equal to integral minus infinity to infinity d times x square del c by del square c tilde by del x square dx. This is what we had. So, we can always define this as u, x square as u, and this as dv dx. So, let us take x square as u and del square c by del x square as dv dx. So, what is this? This will be integral u dv dx dx. So, you can use this formula now to do this integration of this. So, if you look at this carefully, let us write down on the only the right hand side, If you write down the right hand side only, what do we have is that d into integral x square del square c tilde by del x square dx as integral, I call this x square as u and this as dv by dx into dx, and we said that this is just nothing but integral uv in the limits minus integral v du, v du by dx minus infinity to infinity. Now, here u is x square, this we take as u, and dv by dx is del square c tilde by del x square. So, what is v if this is dv by dx? V will be del c tilde by del x. So, the derivative of this will be del square c tilde by del x square. So, you will get this. So, if you apply this formula and rewrite this integral, what you would get is the following. So, look at here. So, you will get u, which is x square, into v in the limits minus integral v, which is del c tilde by x, into dx, u v du, derivative of x square, which is 2x. So, if you apply that formula, that is integrate by parts, do that carefully, you will get exactly this. You apply that formula, take x square as u and del c tilde by del x as v, you will get exactly this formula. Now, what is the derivative at infinity and minus infinity? We said that the derivative at infinity and minus infinity there isn't anything. So, this derivative at both the places will go to 0. So, this term will go to 0, because there is no concentration at infinity and minus infinity. There is no derivative also, because there is no change in concentration either, because there isn't anything at all. So, essentially, or in other words, it is symmetric, whatever on the left side has to be equal to the right side. So, this term will go to 0, and this term will go to 0, and this. So, what remains is just this. What remains is just this. So, del by del t of x square average has to be minus, I take this 2 outside, 2d minus infinity to infinity del c tilde by del x into x dx. So, you have this function now. Now, you can do the same way, integrate by parts once more. So, now let us see what we have in hand. What we have in hand is that, look at what we have in hand. We have in hand is del by del t of x square average is minus 2d into minus infinity to infinity x del c tilde by del x dx. Again, we can do this integrate by parts. We can take this x as u and this as dv by dx. or del v by del x if you want, and you can integrate this by parts by the same formula that we used. And what do we get? What you would get is that, again let us say x is u, so u into v in the limits minus v du. V is c tilde and du is dx, which is 1, sorry, which is the derivative of x, is what dx by dx is 1. So, what you will get is 2d into integral c of x dx. Again using symmetry arguments, and that the concentration anyway at infinities will be 0, you can show that this term is 0. Why is this 0? Because the concentration at infinity and the concentration at minus infinity is anyway 0. So, this term has to be 0. Now, this term is integral 2d integral c of x c tilde of x dx. So, what we have essentially at the end of the day, if you say that this, if you equate this term to 0, because the concentration at infinity and minus infinity is 0. So, if you equate this term to 0, what you have is that del by del t of x square average is equal to 2d integral c tilde of x dx minus infinity to infinity. At the beginning, we said that this is 1, that is the definition of c tilde of, we define c tilde of x such a way that integral c tilde of x dx is 1. So, now what we have, del by del t of x square average is 2d, this is what we have. So, what do we have? Del by del t of x square average is 2d. So, now let us integrate both sides and see what we get. So, what we get is that, so if we have, since this, look at here, since this is integral c tilde of x dx is 1, we have del by del t of x square average as 2d. So, we have x square average is equal to 2 dt. So, you have x square average is 2 dt. This is a very interesting and very important relation as far as diffusion is concerned, very widely used in many contexts in biology and in many places. So, what did we get? We got x square average is 2 dt. We can say x RMS is square root of x square average is square root of 2 dt. What does that tell you? What does this tell you? So, this has a lot of significance. So, let us think about for a minute about the significance of this result. So, look at here this once more, this result. Look at this, x square average is 2 dt. What does x square average means? The RMS or the RMS distance means the average distance that this would go to either side. That is RMS distance this molecule will diffuse in a time t is x RMS. So, what does this mean? If you wait for 100 seconds, so let us say, so let us, d is a constant, t is time. So, we know that let us take for example, so let us take this x RMS is equal to root of 2 dt. This is a very famous relation. Now, let us see what is it. Let us take d is equal to, so what is the unit of d here? D will have a unit which is, so let us take d as 1, let us say it is meter square per second. This will have a unit of meter square per second, diffusion coefficient has a unit of meter square per second. We will come to this, we will see how this is coming, but for the moment let us take d as some number which is 1 meter square per second given to you. Now, the question is, let us say when t is equal to 10 second, how far this would have diffused. So, x RMS is equal to root of 2 into diffusion is 1 into 10. So, this will diffuse the distance of root 20 meter. Root 20 meter. Now, let us say after 100 seconds, when t is equal to 100 seconds, how much this will have diffused? When you take t equal to 100 seconds, what you get? X RMS is equal to root of 2 into d is 1 itself, this is 100. So, you know this is 200. So, what is this? This is square root of 2 into 100. So, 100 square root of 100 is 10. So, this is essentially what do we get? Root of 200 meter. So, this is root of 20 and this is root of 200. So, now we can write root of 200 as 10 into root 2. So, this you can write root 10 into root 2 and this is 10 into root 2. So, we see in this particular way we can calculate how much distance it will travel in time t. If it is 100 seconds, it would have gone. So, you know root of 20, what is root of 20? So, this is like root of 16 is 4, root of 25 is 5. So, root of 20 is somewhere in between 4 and 5. So, let us look at here. So, first case, first when t is equal to 10 second, we get x RMS is equal to root of 20. We know that this has to be 4 point something, because root of 25 is 5, root of 16 is 4. So, this is 4 point something. Calculate it yourself what is root 20 and what is in 100 seconds, that is the time changed by 10 times. If you wait 10 times longer, it would have diffused a distance root of 200. What is root of 100? Root of 100 is 10. So, what root of 100 is 10. So, this is little above 10. So, root of 15. So, this is some quantity much larger than that. So, this is basically what you get. You can write it as root of 200 can be written as root of 2 into root of, sorry, this is wrong. So, what will be this number? This number will be like something between very close to 15, because we know that root of 225 is root of 200 is, so this is something close to 15. So, this is some number which is very little less than 15. So, calculate this number yourself. So, even though the time increased 10 times here, it did not travel 10 times, it only traveled much less than 10 times. So, this is what essentially it says, even though the time increases by 10 times, the distance travelled will be much less than 10 times. So, let us take another example. Let us take, so what we have is x RMS is equal to root of 2 dt, and let us now calculate let us ask the question. So, let us do in another way. Let us t is equal to x square average. So, this is what we had, 2 dt is x square average. So, let us say t is equal to x square average by 2 d. So, now let us ask the question, if we can, you can ask the question again, do it yourself, ask this question, if you want something to diffuse, let us say if it is diffuse 1 micron, let us take the example of some more protein molecule, let us say actin molecules, and ask the question, what is the time it takes to diffuse 1 micron, and ask the question, how long it will take, how much time, how long it will take to diffuse twice the distance, that is 2 micron. So, such kind of things can be calculated from what we learned so far. So, just like what we did now, we can also calculate x average, which we will discuss later, but this is a very important relation which we used in many different places, many different occasions, both in biology, chemistry, physics, chemical engineering, any field you take, pretty much this relation is used, that is the x square average is 2 dt. If, and this is a very important consequence, and anything that will diffuse, if you wait 10 times longer, it will not go 10 times farther, it will only go much less than the 10 times, much less than 10 times. So, that is the whole message. We just saw that if you wait 10 times more time, the distance that will be traveled will be much less than the 10 times. So, essentially, what, to summarize the lecture, what we learned today is a very important relation. So, this is our summary, just one equation, x square average is 2 dt. So, this is our summary for today, because this is a very important relation in biology, in physics. If you have learned spectroscopy or many different areas, you might come across this relation. So, just realize that without solving the diffusion equation, we started from this equation. Without solving this equation, by doing a trick, by just realizing that at infinities the concentration will be 0, we found that x square average is 2 dt. So, with this important relation, we will stop today's lecture. We will continue a little more about diffusion in the coming lecture. And there is another important relation. We will discuss this in the next lecture. So, for this lecture, let us stop it here now. Bye.